Okay, last lecture, the one that we did in lab, we talked about nomenclature. We rushed through naming binary ionic compounds, so where we have just two things. One of those things being a metal ion. We've got two different types of metal ions. Remember, we've got our main group metal ions. Those are the ones in the far left 2 columns and the far right 6 columns. And we also have scandium, zinc, and silver that also have reproducible ion charges. Scandium, Sc being +3, zinc and silver being +2 and +1 respectively. So we write the name of the metal ion. For a lot of things, that's just the name. For things where it can have multiple charges, things where we don't know the charge all the time, it's the name with, in parentheses after it, the charge in Roman numerals. Or it's something like ferrous, ferric, stannic, stannous, something with that IC or OUS ending. Then we also have the base name of the anion and change the ending to "-ide", or it's an oxyanion, in which case we don't change the ending to "-ide". We also talked about naming binary molecular compounds where we've got the prefix and then the first element. Remember that we omit if that prefix is mono, if we've just got one of that element. Then we've got our prefix for the second element plus the base name, change the ending to "-ide". Today what we'll be covering is acids, oxyacids, organic naming, some molar mass stuff, and some calculations relating to molar mass and counting the number of molecules or units of a compound. So first, we'll start off with naming acids. Acids are molecular compounds. Molecular compounds meaning that they are nonmetals only. And they release hydrogen ions when dissolved in water. This is a key fact about acids. Release hydrogen ions, H+, when dissolved in water. If they're not dissolved in water, they're just a molecular compound, and they wouldn't be an acid, or acting as an acid in that case. Acids are composed of hydrogen, which is typically written first in the formula. In my classes, we always write the hydrogen first if it's an acid. That's just to help you. It's less memorization. And there's usually one or more nonmetals written second. For example, HCl is a molecular compound. Hydrogen is a nonmetal. Chlorine is a nonmetal. When dissolved in water, it forms H+, aqueous, and Cl-, also aqueous. That's chloride. Remember that aqueous, AQ, means that it's dissolved in water. If that's there, it's an acid. If it's not there, then technically it's not an acid. I usually don't make that distinction. I just talk about anything that can act as an acid. But strictly speaking, it's not an acid if it doesn't dissolve or if it's not dissolved in water. Some characteristics of acids. Acids tend to have a sour taste. Think first they're sour, then they're sweet. Sour Patch Kids? I couldn't remember the name, but I could remember the logo for some reason, the phrase. Acids will also dissolve many metals, things like zinc, iron, and magnesium, but good for us, they don't dissolve gold, silver, or platinum, usually. Other precious metals also often don't dissolve in acids. The formulas start with H. So things like HCl, H2SO4, other things like that. Some acids, you can write them with the H's in front. There's also a version sometimes where you don't write the H's in front. I usually write them with the H's in front so that we can easily identify that they are an acid. So acids, their formulas start with H. For naming acids, we've got two options. We've got binary acids. They're composed of hydrogen and one other thing, a nonmetal. Oxyacids contain hydrogen and an oxyanion. So I think this is a relatively simple split. For our binary acids use the prefix hydro. So when we are naming them, they start with hydro, always. And they will also have acid added onto the end. So our formula is we start with hydro, we have the base name for our nonmetal, we change the ending to IC and add acid to the end. These I think are relatively simple to name, especially compared to our ionic compounds. So if we want to write a name for HF, it's aqueous, so we know it's an acid or it's acting as an acid, we'll name it as such. It starts with H. Starts with H, so it must be an acid. And it's just two things, it's binary. So we're going to start off the name with hydro. And then F is fluorine. The base for that is fluor. We change the ending to ic, and we add acid to the end. So HF aqueous would be hydrofluoric acid. In the base name for fluorine, which vowel comes first, U or O?
U.
U comes first. It's not hydrofluoric acid. We can't bake with it, or we shouldn't bake with it. Hydrofluoric acid, also famously the acid that they used in Breaking Bad to dissolve the bathtub. If we wanted to write the formula for hydrosulfuric acid, we can also do that. We would hopefully see that it starts with hydro and it ends in acid, some good signs that we're dealing with an acid. The acid's the dead giveaway. The hydro lets us know that it's binary. So it's just two things. So we're going to start our formula off with hydrogen. The base for hydrosulfuric acid is sulfur. What charge does sulfur have when it's an ion?
2 negative.
It's a 2 minus. We know that because of the column that it's in, the group that it's in. It's in the 6A or 16 group. And it's going to have the same number of electrons as the nearest noble gas, which is 2 spots shifted over to the right. That means adding 2 electrons, so 2 negative charge. If our hydrogen ions have 1 plus charge and our sulfide has a 2 minus charge, then that means that we need, if we crisscross it, H2S. That would be our full formula for hydrosulfuric acid. Any questions about binary acids? So when we're going from the name to the formula, the number of hydrogens, I'm going to write it out because I don't like the predicament that was putting me in. Number of hydrogens is equal to the charge on the nonmetal. We'll see a similar thing happen with oxyacids. With our oxyacids, so we have an oxyanion. The oxyanion has a charge. We'll also need a number of hydrogens to balance out the charge on the oxyacid, or on the oxyanion. So for our oxyacids, we need to identify the name of the oxyanion. So this is if we're working from the formula to the name. So we will find the oxyanion's name, either from our memory, or if we haven't memorized them yet, working through with our green sheet to find the oxyanion that has the same nonmetal base other than the oxygen, and then counting based on how many extra or fewer oxygens it has. And then we make a change to the name of the oxyanion. If the ion ends in ATE, we change that ATE to IC. So ATE turns into IC when it's an acid. And if it ends in ITE, it turns into OUS. And the prefix, if relevant, if there's a prefix in front, if there's a per or hypo, we just leave it alone. We don't do anything with it. So ate to ick, ite to us, and we add acid at the end. So the hardest part about naming oxyacids is having the oxyanions memorized. Once we have the oxyanions memorized, relatively easy to do the naming. Ate to ick, ite to us. So if we want to name HNO2, which part of HNO2 is the oxyanion? NO2. Yeah, it's the NO2. So this is our oxyanion. And we would either in our brains or from our green sheet find the ATE ending, the 8 version of the nitrogen oxyanion. Nitrate is what that would be. It would be NO3, the 1 negative charge. We can tell the charge also from the number of hydrogens in the front. So nitrate is NO3 minus. We've got NO2. It would be a 1 minus, but we've got the hydrogen there. So NO2, how is that changed from NO3? We've lost 1. We have NO2 minus, which would be 1 fewer oxygen. And we change the ending when we drop 1 oxygen to ite. So we have nitrite. So knowing that we've got nitrite, we start with the NITR, that's the base. We have to change the ite to something. What does the ite change to? Us. Changes to OUS. And then we add acid to the end. So this would be nitrous acid. Again, it's 8-ic, ite us. If you eat something, sometimes it's gross. That might be an ick. Right? I ate it. Ick. Gross. Ite us. I don't know. Just make that your little oxyacid mantra. 8-ic, ite us. 8-ic, ite us. 8-ic, ite us. You can just repeat it to yourself until you have it memorized. All right, working the other direction, we've got perchloric acid. So we've got definitely an acid because it's got acid in the name. And we've got perchlor, and that ick we would have gotten from what? What would the ick have come from? Ick came from 8. We're just working the opposite direction. So we've got the perchlorate oxyanion. So we have to take the name perchlorate and come up with a chemical formula. So we would think chlorate, what is chlorate? We would either pull it out of our memory, we'd refer to our green sheet. Chlorate, yep, is ClO3 with a 1 negative charge. We have perchlorate. How does the per affect our ion?
1 extra oxygen.
It adds 1 extra oxygen. So perchlorate is ClO4 minus. If we've got a 1 negative charge, how many hydrogen ions, H+, do we need to balance out our 1 negative charge? 1. So we need 1 H plus to balance out. So our equation would be HClO4, or our formula would be HClO4. So the hardest part, I think, for most of us is probably just going to be having the ions memorized. You are expected to have the ions memorized. There's a sheet in the lab manual that says ions to memorize. You do have to have, you're expected to have all those memorized. So if it's on there, it's not something that you would be given on an exam. Like, I wouldn't tell you what the name is on an exam. I would expect you to know it. This is just a run through for writing the formulas for acids. We've done this twice now. So when the name ends in acid, the formula is going to start with an H. We should associate acid with H. We'll write the formula as though it's ionic, so using charges. Even though it is classified as a molecular compound. If we have the hydro prefix, that means it's a binary acid. No prefix or a per or a hypo means that it's an oxyacid. And then for oxyacids, it's the same ate, ick, ite, us, just working the opposite direction. So we'd revert the changes. If it's ick, it goes back to ate. If it's us, it goes back to ite. Then write the oxyanion formula. Once we have the name, crisscross charges on H plus and the oxyanion, and then it should be balanced. You don't necessarily have to do the crisscross thing because it's always going to be a 1 plus for our hydrogen ion. So it's just going to be the number of hydrogen ions will balance out the charge on the oxyanion. Any acid questions? Cool. Some more acid examples. Hydrocyanic acid is one that doesn't exactly follow our binary naming convention, but we still use it like it's a binary. And then we've got a couple of oxyacids. I'll give you some time to give these a shot, and then I'll go over them quickly. All right, hopefully enough time to get at least one of them done. So we want to write formulas for the following acids. We first got hydrocyanic acid. What kind of compound is hydrocyanic acid? It's an acid. It is, because of the hydro, a binary acid, or it uses the binary acid naming convention. That means we're going to have hydrogen and something that's not an oxyacid, essentially. And we've got this blue-colored base name, cyanic. This is from cyanide, which is Cn minus. So that's our anion. Our formula is going to be HCN for hydrocyanic acid. And then we've got phosphoric acid, also an acid. What kind of acid do we have? It's an oxyacid. We don't have the hydro in front, which lets us know that it's an oxyacid. So we are looking for something with phosphorus in it for our oxy anion. PO43 minus is phosphate. So that's the first oxy acid that should come into our heads. We have in our name the IC ending. What does IC come from? IC from 8. So that means that we have phosphate for our oxy anion for phosphoric acid. So PO43 minus, we're going to balance that by adding hydrogens in front. The 3 comes over. It's H3PO4 for phosphoric acid. And then we've got hypochlorous acid. Hypochlorous acid is also an oxy acid. The hypochlorous, the chlor base, should make us think chlorate. ClO3 minus is chlorate. We have the oxy anion that's got the hypo prefix, and we had changed it to the OUS ending. That OUS ending comes from the ITE. It turns into OUS, us. And the prefix stays on there as well. So what we have is hypochlorite. So we have to figure out how many oxygens do we remove to get from chlorate to hypochlorite. The first oxygen that we remove is chlorite. So ClO2 minus would be chlorite. And then we could add to the front the hypo prefix to take off one more. So it would be ClO minus for hypochlorite. And then to balance out the one negative charge, we just need one oxygen in front. So HClO would be hypochlorous acid. Any acid questions? I'll also very briefly point out why we have to use that hydro. If we have HCl and HClO3, HCl is hydrochloric acid. Let's just take off the hydro, pretend like it's just chloric acid. HClO3, ClO3 is chlorate. How does the ending of chlorate change when we turn it into an acid? 8 turns to what? Ic. So this would also be chloric acid. So if we don't have the hydro prefix, that makes it impossible to distinguish between these two. So that's one of the reasons maybe that we have that hydro prefix. It is important because otherwise it could be something else. For overall inorganic nomenclature naming, you can basically just use this flowchart, but you will not have this on the exam, so I recommend figuring out the way to make these ideas stick into your brain. So the way that this flowchart works is we have to first identify what the compound is that we're dealing with. Is it ionic? Is it molecular? Or is it an acid? Remember that our acids start with H, our molecular compounds are nonmetals only, our ionic compounds have metals and nonmetals. And some of these split. So our metals that form one type of ion only, mostly our main group elements. It's just the name of the cation, change the base name of the anion to have "ide" at the end instead of "ene" or "ogen" or whatever else it might end with. If it forms more than one type of cation, then we have the charge of the cation in Roman numerals after the name of the metal. Or whatever the old name for the cation might be. Because we also have to know some of those. For our molecular compounds, that's our nonmetals only, we've got prefix, name of the first element, prefix, name of the second element, change the ending to "-ide." And we omit mono for the first prefix. And we just covered acids, so I'm not going to talk through all of that again. So this would be a helpful flowchart. If you need to reference something when you're working on the nomenclature worksheet, I would recommend trying to do the nomenclature worksheet as much as possible without referring to your notes. That way you're testing your memory a little bit. Give yourself some time to struggle before referring to your notes, and then check your notes, of course, if you need to. I expect that you're going to need to use your notes a little bit, or a lot of it. And now we're going to jump to organic compounds to make sure that we cover those, and then we'll come back to the math stuff at the end. So we have been talking about inorganic compounds. There's also organic compounds. Organic compounds, basically, we're just going to be covering for this one section. They'll come up a little bit later in the class, but for the most part, organic compounds are siloed into this one exam module, essentially. So early chemists divided things into organic and inorganic. Organic compounds come from living things. Things that come from non-living things got called inorganic. So think rocks and dirt. They found that organic compounds decomposed fairly easily compared to inorganic compounds. They were able to synthesize inorganic compounds in the lab, but organic compounds were not so easily synthesized. Today, organic compounds can be made pretty simply, pretty easily. We're good at chemistry now, relatively speaking. So we can make them in the lab. We find them all around us. It includes some medicines. Organic compounds are composed of carbon and hydrogen with some other elements in there, but carbon is basically the backbone of organic compounds in organic chemistry. So the key to organic chemistry is carbon. So like in things like methane, CH4, we will often draw out the structural formula rather than the space-filling model because it's so much easier to draw. So organic compounds typically have carbon in them. Carbon bonds in organic compounds are almost exclusively covalent. They're actually sharing their electrons like they were supposed to, like they learned in kindergarten. When carbon bonds, it forms 4 covalent bonds. Carbon forms 4 bonds. Just a general rule of thumb. It will almost never have more or less than, fewer than 4 bonds. And this is total bonds. So a single bond counts as 1, a double bond counts as 2, a triple bond counts as 3. It can bond with other carbons, or it can bond with hydrogens and other things. And because carbon loves to bond to other carbon molecules, it can form chains, it can branch out, it can form ring structures, it can form double ring structures. It can get really cool and complicated and weird. And we need to be able to name all of them and be able to talk about exclusively the one thing that we're trying to talk about. So the naming for organic chemistry gets really, really complicated. Again, we're mostly working with this in this section, and it won't really travel that far out of this section. So carbon bonding, this is like the full structural formulas. We've got a bunch of different compounds, things like propane, isobutane. We've got an acid, ethyne. Normally, when we draw stuff in organic chemistry, hydrogens get omitted because there's a lot of them. So the hydrogens are usually not drawn in. And the assumption is every carbon has 4 bonds. If it's missing bonds, You just pretend like there's hydrogens on there to make it up to 4 bonds. So some examples. If we look at this far left carbon in this propane, it's got 3 bonds with hydrogen. So 3 hydrogen carbon bonds, and then it also has 1 carbon-carbon bond for a total of 4 bonds. We can also do this in ring structures. And if we've got double bonds, look at this right carbon. This right carbon has 1 double bond with carbon. And it also has, on top of that, 2 hydrogen carbon bonds for a total of 4 bonds, or 4 lines. Each of the lines represents 1 bond. In ethyne, it's the same thing. We've got a triple bond between the carbons, and then they have 1 extra bond on top of that. So that's our 4 bonds coming into play. It's always going to be 4 bonds for carbon. Hydrogen will always have 1 bond. For our hydrogen, or our hydrocarbons, we can have either hydrocarbons. Hydrocarbons are just hydrogen and carbon. That's what makes them hydrocarbons. And then functionalized hydrocarbons, we're really putting the fun into this, also has what we would formally call heteroatoms, things that are different from carbon and hydrogen. So other elements like oxygen, nitrogen, sulfur, phosphorus, etc. Just anything that's a nonmetal and not hydrogen or carbon. So our hydrocarbons contain only carbon and hydrogen. They're commonly used for fuels. Things like oils, gasoline, liquid propane, and natural gas are all examples of hydrocarbons. For naming hydrocarbons, it's relatively simple for organic chemistry's sake. If we have only single bonds, then these are called alkanes. So only single bonds, we've got alkanes. If we have any double bonds, then these are alkenes. So from anes to enes. And if we've got triple bonds, then it's ines. With a Y. So we've got alkynes. And our naming for these is we're going to have a base name. The base name is determined by the number of carbon atoms. There are lots and lots of options based on the number of carbon atoms. And then we'll have a suffix based on the multiple bonds. So if there's single bonds, double bonds, or triple bonds, then we get changes to the endings. And this is showing up on the next slide as well. So if you miss it, don't worry. So our base name depends on the number of carbon atoms, and then the suffix is determined by the types of bonds. So alkanes end in ane, alkenes end in ene, alkynes end in ines, Y-N-E, for their names. For our base name, the first couple confusing, and then after that it goes to something that we probably recognize. So our first one is meth. And I'm going to draw arrows to the ones that are weird. We've got meth, eth, prop, bute. The first four are weird. And then after that, pent, hex, hept, oct, non, dec. Those are the same as the prefixes that we use for our molecular compounds. And these are the number of carbons. So after you get past the first four carbons, then it turns into basically just molecular compound prefixes. So we use one of these bases, and then we'll add ane, ene, or ine, depending on what bonds we have. Here's some common hydrocarbons. So some options. We've got methane, the meth prefix letting us know that we've got one carbon, which we can see in our molecular formula. It's all single bonds because it's only one carbon. It can't form double or triple bonds, so it's always going to be methane. The ane ending meaning it's all single bonds. For propane, like you'd use in an outdoor gas grill typically, that means that we've got three carbons. The ane ending letting us know that we've got all single bonds. So we've got carbon bonded to carbon, bonded to carbon. They'll always form a carbon chain. And then we've got our hydrogens added on to get them all up to 4 bonds. We've also got N-butane and N-pentane. The N part on the front, I'll talk about in a sec. So the bute means 4 carbons. We can see that in our structural formula, the 4 carbons. The ane ending meaning that it's all single bonds, and we can see that it's single bonds between our carbons. The N that gets added to the front, the N is for, I think it stands for normal, but it basically means that it's a straight chain. So they're all lined up. There's no branching happening. When branching occurs, we get to have more fun. But not as much fun as when we're functionalized. And then some examples of the ene and ine endings. We've got ethene, the eth prefix or base, meaning 2 carbons. The ene, meaning we've got a double bond. In ethyne, the eth base, meaning that we've got 2 carbons. The ine, meaning that we've got an alkyne or have a triple bond.
So butane and pentane could have different structures?
Yeah, so butane and pentane with 4 and 5 carbons respectively could have branching that occurs. Like isobutane or isopentane or other names. Propane is that's the outdoor gas. There's also an alcohol form of that, propane, propanol, or isopropanol. Those are 2 different forms of the alcohol that you form with propane. Which brings us to functional groups. So functional groups, emphasis on the fun, functional groups derive from the added functionality that adding a new cluster of characters in there imparts to the overall organic compound. Sometimes you might see double or triple bonds called functional groups because they also change the way that the compound behaves. A group of organic compounds that have the same functional group in common forms a family of organic compounds. For example, methanol and isopropanol are both members of the alcohol family. They both have alcohols in them. And we've got some written out formulas. So the meth prefix, or the meth base, methan, meaning that we've got one carbon. So we're still using our base names, meth, eth, prop, bute, etc. But because we've got an OH functional group, this OH is the alcohol. So OH is the alcohol group. And when we have the alcohol group, we change the ending to ol, O-L. So methane, because we've got methane, but we swapped out one of the groups for the alcohol, so it's methanol. Isopropanol, because we've got isopropane, sort of, it's related, or 2-propanol. We've got the propane part, propane, 3 carbons with single bonds only. We change the ending, the E at the end, changes to an OL because we've got the alcohol on there. Isopropanol means that the alcohol group is attached to the middle carbon. 1-propanol, or if you just said propanol, we would assume that it's attached to one of the end carbons. We've got a bunch of different families of organic compounds that we'll talk about very briefly. We've got alcohols, which we just talked about. So those have the name ending in OL. And the general formula is whatever our alkane is, R here just generally stands for alkanes or whatever the rest of the molecule is. You just put anything where you want the R. So if it's got that OL ending, that means that it has an alcohol, an OH. We also have ethers. Ethers are an oxygen that's stuck between bridging 2 carbon groups, and you add ether to the end. It's like in this one, diethyl ether. The ether part meaning that we've got this oxygen in the middle. Diethyl, ethyl is when we've got eth, 2 carbons. The YL meaning that it's like an added group. The di at the front meaning we've got 2 of them. So 2 ethyl groups. 2 carbon groups that are bonded in there. Aldehydes end in AL. Aldehydes have this important group. So we've got carbon double bonded to an oxygen and also bonded to a hydrogen, and this would replace with whatever you want for an alkane. And these would end in AL. These usually smell sweet or nice. So ethanal, the ethan part for our 2 carbons, the AL ending because we've got the aldehyde on there. We've got a related group called ketones. Ketones end in -one, and now it's that carbon bonded to a double bond, but it's between 2 carbons. So it's bridging two carbons rather than being a carbon and a hydrogen. This one, our example, we've got 3 carbons. So that's the propan part. 3 carbons, we change the ending to -one because it's that ketone group in the middle. We also have carboxylic acids, which are a type of organic acid. They generally are weak acids. And the acid group is, we've got our alkane bonded to carbon, and the carbon has a double bond with an oxygen, and it also has an alcohol group. So it's got both of those things at once. And we've got an example with acetic acid, so this is the one that you'd find in vinegar. You could also call this ethanoic acid. I think would be the name. The ethan, because we've got 2 carbons. The oic, because it's an acid, so we change the end to ic and add acid at the end. We also have esters. Esters are like the carboxylic acids, but instead of the hydrogen, we've got another alkyl group or another carbon or something else attached to it. So COO and then whatever else comes at the end. And we've got methyl acetate. Acetate is the name for basically the acetic group. So that's this part would be the acetate. This would be the methyl part. As you can probably tell, the naming is very fun and not confusing. I'm being very sarcastic there. It's very confusing. We can also have amines, and amines have nitrogen. So this is ethylamine. Ethyl because it's 2 carbons, and then the amine part is nitrogen bonded to however many hydrogens it needs. And I can talk about these compounds in more length in lab, but I don't have the slides prepped because I was not expecting our nomenclature to be so buffed up. And some other things, I have to put a mark so it'll make an extra page. We also can have cyclo as a prefix. Cyclo means the compound has a ring structure. And that ring structure is the carbon chain. So let's say that we've got 6 carbons, and it's all single bonds. That would be hexane. If we drew that out, we would have 6 carbons. This would be N-hexane, because it's the straight chain version. I'm omitting the hydrogens because I don't want to draw them. So this is hexane. If we have cyclohexane, then instead of being a chain, the carbons are bonded to other carbons in a loop or a ring. So that's the cyclo. Cyclo, like cycle, like something that's round. Other stuff that we should know for naming organic compounds. For alkanes, I don't want to get into functional groups at the moment. Names are based on the longest chain of carbons, or the longest carbon chain. So it's possible that we've got carbon bonded to carbon bonded to carbon, but we draw it out like this. So we've got a branched structure. We have only single bonds, so it's going to end in ane. What's the longest chain of carbons that we can make? How many carbons can we chain together? 4. 4 is the longest that we can have. Instinctively, we might read, oh, 3 carbons. Prop is for 3, so we'll call it propane, and then we'll figure out what this additional group is. But it's actually longer to count it this way. So in the nomenclature worksheet, there's several branched examples with alkanes. You have to count out, figure out what's the longest map that I can make. So this is 4 carbons, so this would be some variant of butane. So butane is the base, and then the way that we name these extra bits that are attached on is we have to first specify where they're located. So specify branch locations. With a number. So we have to number our carbon chain. So we need to number these carbons, 1, 2, 3, and 4. There are 2 ways that we could number it. We can number it left to right, which would give us those labels. The other option would be to label it right to left. One of these is correct. The one that's correct is the one that gives us the lowest number on our branched group. So number carbons to minimize branch numbers. We want them to be as low as possible. When we're just talking about branched alkanes, alkenes, alkynes, might actually just be alkanes. The rules get more confusing when we add functional groups in, or more complicated. So redrawing this, carbon to carbon to carbon to carbon, and we had our one branch on the second carbon. So the correct numbering here would be 1, 2, 3, 4 from left to right. So which carbon is our little add-on attached to? 2. How many carbons is the branched group? This little add-on. 1 carbon. Does anyone remember a prefix or a base for 1 carbon? Meth. 2 meth. And then to let us know that it's an add-on group, that's where the YL comes in. So 2-methyl. This whole thing is to specify that carbon. And then our base chain is how many carbons? 4. And what's our base for 4? But, or but. And we have all single bonds. So that but, or but, is for 4 carbons. And then the ending is ane, A-N-E, because it's all single bonds. Question?
Did you get the YL?
The YL is to let us know that it's a substituent group, it's an add-on. It's not the main character. Other questions? Yeah.
For the while end of that, would we use any other like prefixes syntax or just while numbers add?
You would just add the YL at the end. That's if it's 1 carbon, 2 carbons, 3 carbons, 100 carbons, however many it is, you add the YL at the end to let us know that it's a side group. We can also have multiple groups. So if we've got 2 groups, 2 carbons, our carbon chain is still 4 carbons, so it's still going to be butane for the base. But now we've got 2 groups. Where's one of our groups located?
On top.
What carbon is it located on? It's on the 2. Where's our other carbon group located?
On the 2.
Also on the 2, so 2 comma 2. And how many of those groups do we have?
Meth.
They're both meth. How many do we have?
1.
We have 2.
With 2.
2 on the 2. So we use the di prefix. So we do have prefixes, which gets back to the question that we had. So di because there's 2 of them. The 2 comma 2 is letting us know that they're both on the second carbon, and they're both methyl. So 2,2-dimethylbutane. I'll give us a practice problem. I'll give us 2. How about that? It's di because we've got 2 groups and they're both meth. They're both 1 carbon groups. Because we've got this carbon on the bottom, this carbon on the top. They're 1 carbon each, but there's 2 of them. 2 separate groups. If it was 2 carbons in a row in a chain, then it would be F. So let's come up with the names for some hydrocarbons. We've got that one, and I'll give us one that's a little more fun. Some might even say it's too fun. All right, our first one, our blue one, our top one. What is the longest carbon chain that we can form? How many carbons can we line up?
4.
4. I drew it out in a way that we can number them from left to right. 1, 2, 3, 4. You could have also chosen to start with the up or the down. That would also be fine. So 4 is but. We have only single bonds, so it's the ane ending. Butane is our base. It's not just butane, though. We've got 2 extra things added on. Where is one of those things located? Which carbon is it on? We've got one on the 2. Where's the other one?
3.
On the 3. So we've got on the 2 and on the 3. And I'm numbering it 2, 3 because they are together. They're the same thing, rather.
That's how you number.
What are those side groups? Meth.
Methyl.
So 2, 3. Di because we've got 2 of them.
Okay.
Methyl. So that'd be 2,3-dimethylbutane. Because one of our methyls on the second carbon, one of our methyl is on the third carbon. And then for our second one, our red one, what's the longest carbon chain that we can string together here? 6. So that is our longest carbon chain. Our instinct is probably just to read left to right and catch this 5 carbon length chain. But if we go the side route, we can get 6. So our base on this is going to be hexane. And then we have to figure out how we are going to number our 2 add-ons. What is one of our add-ons? What would we call the group? Either this one or this other one. What's one of them called? Methyl, ethyl, propyl, butyl.
Ethyl.
We've got an ethyl. And the other one is methyl. Since these are 2 different groups, we don't label them together in terms of their numbering. So we can't do like we did here, 2,3-dimethyl. They're different groups, and so they each get their own separate number. We have to figure out what numbers to give them. So I'm going to draw out both ways that we can number this, and I'm going to straighten out the chain for us. So we had one there, and we had one there. And if we were labeling it left to right, 1, 2, 3, 4, 5, 6. So what would our numbers be for, let's start with our methyl group. I don't actually remember which we label first. Let's assume that we put the methyl first. So what's the number of carbon that the methyl is on? 5. So it's going to be 5-methyl. And then what's our other group?
3 is
It's the ethyl, and it's on the third spot, so 3-ethyl. And the base is hexane. So this is one possible option. Let's look at if we label it the carbons the other way with the tools that I have. So doing my best to do a mirror image. This is so that we're labeling it left to right. Again, you can just label it the opposite direction. That works too. I don't know which is less confusing. So this is the same thing. I've mirrored it left to right. And now what number would our methyl be on? So this would be 2-methyl. And now where's the ethyl? 4. So it'd be 4-ethyl. And it's still hexane. So those are the 2 possible options that we can come up with. Which one gives us the lower numbers? The top one or the bottom one? The bottom one, the second one. So this gives us lower numbers. This is the correct version. We need the lowest numbers possible. Yeah, question?
So will that determine like whether we read it left to right? Just trying to find the lowest numbers out of the 2?
Yeah. And it's more confusing when we've got a ring. Then you have to pick which carbon you're starting from and which direction you're going.
Does it matter which one?
It does. There's always a correct way. Alcohols use the same numbering here. same numbering sort of system that we're using here, but the number would go before the all at the end. And I'll draw us an example of that so that we have one. That kind of looks like I wrote OK. So butan 2 all. That's the modern naming. You will also probably more frequently you'll see 2-butanol. The modern naming is that we put the number right next to the group. And the old / more common version is to put the number at the front. I don't think that there are any multifunctional group questions on the nomenclature worksheet, but you can have like, what if I've got 2 or 3 or more alcohol groups? What if I'm combining 5 different functional groups and I've got a ring structure and there's double bonds? There's rules for all of that. If you just take a look at the Wikipedia page for organic chemistry naming, not because it'll help you, because I don't think it's helpful, but just to see how crazy it is. It's like the most ridiculous thing you've ever seen in terms of like. Are you talking about this middle?
Yeah. Like one carbon pokes out on the
Yeah, so
by itself.
because they're different lengths, that's why we can't use the di. Because we've got one methyl group, we've got one ethyl group.
And then once they both have like the same amount of bonds on the outside, then you use that.
Yeah, so if this bottom one, instead of being an ethyl, is a methyl, then it would be 2,4-dimethyl to show us where both of our methyl groups are. All right, we'll stop there.